This is a tutorial about how to define the frame in RAPT. We're starting off with the file that we created in the tutorial introductory RAPT run. So I'll open that now. And we are now going to the frame section. So we'll start with spans. We originally created a frame that had 8 meter spans, 300 millimeter left end and right end, 200 millimeter fixed slab in all spans, and a 5 meter tributary width or panel width. The panel width defines the loading that is applied to either the column strip or the effective width of the beam that's being designed. And the other thing to note in this panel is if you want to design anything that is more than just a left end, so in other words a left cantilever, you have to define that as a left cantilever. So you right click here and you say change to left cantilever. Now it's automatically grown that to something that's to a dimension that's more reflective of a cantilever, but you can change that to anything you want. And similarly with your if you were to have that as a left end, you can make that left end 2 meters. But when you have a left end, RAPT stops the flexural calculations after the column grid line. So this doesn't apply any counterbalance to this part of the span. It is just used to develop bars. So RAPT just uses that space to calculate the development of bars. If you want that to be calculated as part of flexure, you have to create that or change that to a left cantilever. I'm going to leave it as a left end for now. Usually left ends match the column, the smaller of the column widths. So below we have a 400 by 400 column, and so the slab, or I mean the left end is extended by 200 millimeters, which is half the width of the column. Moving on to, now the other thing is we can delete and remove spans. So if I right click here, I can delete a span or I can add a span, and you can add one or many more spans, and then RAPT will add that for you, and it will adjust any existing reinforcement or PT that you've already got in your run. I'll delete that for now. In the column space, we can define first of all grids. So grids are at the moment 1, 2, 3, 4, 5, and 6, and we can make that A, B, C, D, E, and F, and you'll see that they are reflected in the grids below. I'll change that back. The column we can have a column or we can have a pin support. If we have a column, we define the column height. If we have a column diameter, then any parameters for a square column are turned off. But if I zero this, you'll see that the dimensions for a square column come up. And so now we have a square column 600 by 600 on the first grid here above. So if I go into plan, that'll be reflected a little bit more accurately. So there it is, there's our column above, column over, column over. I'll change this back to what it was originally. To change it back, I zero out the rectangular columns and I put in the diameter of the column. Same goes for column below. And then we have our transverse column spacing. The important thing to note with RAPT is that RAPT is based on the equivalent column method. And the equivalent column method is a method to calculate the bending moments that can be transmitted into the columns. So if we were to look at this slab here in plan, we can see that the beam can transmit a bending moment into the column at the face of the column. But there is also a portion of bending moment that's transferred via a torsion strip on either side into that column. And the equivalent column method is all about calculating how much that torsion strip can transmit. There are many textbooks with more information if you want to know more. This transverse column spacing affects that equivalent column stiffness and how much torsion, how much moment can be put into the column. So the equivalent column method relies on a number of inputs in terms of the equation to calculate that torsion moment or the effectiveness of the torsion strip. And one of those numbers is the length from this column to the next column, including the slab thickness and any transverse beams if there are. So that affects that number. You must put your transverse column spacing in accurately. Next, you can set a column capital. This is just a simple column capital, which is at a 45-degree angle. So if I was to add in a 1 meter or 500 millimeter column capital, you'll see that RAPT will add that to column grid 2. And there it is. We don't want any column capitals for now. If our slab is on columns and those columns are on pad footings, then we would pin the base. If it's sitting on top of another floor, then we would assume that that floor is fixed. We can also adjust the effective stiffness of the column, and you would usually adjust that to bound your analysis. So you might have something like 80 to 100% for your ultimate limit state, and maybe you'd have something like 60% for your deflections. This here is whether or not there is a horizontal restraint in your slab. So you might have a core or a shear wall somewhere that is not defined in RAPT. RAPT doesn't do cores or shear walls. So you must tell RAPT if there is a horizontal restraint. If there is, it affects the bending moment in the frame. And RAPT undertakes an elastic frame analysis, 2D frame analysis, and that 2D frame analysis generates bending moments, and that bending moment diagram for the frame changes if you have a fixed lateral support at the slab. So you must be aware of that if you have a lateral, if you have a laterally stiff element attached to the slab. This is whether or not you would like column shortening to be calculated. By default it is, but be aware that column shortening is only calculated for the column immediately beneath, not for total column shortening. For example, if you're on the 30th story of a building, it doesn't calculate the shortening below all 30 stories. In the same vein, it also just calculates elastic shortening, not creep and shrinkage. This is whether you want a punching shear check. By default, it's turned on. This is the punching shear effective depth in the transverse direction, because your reinforcement in the transverse direction will be at a slightly different level to the longitudinal bars. And this is your transverse P on A or transverse pre-stressing, average pre-stressing stress. Also affecting your punching shear. If you were using Eurocode or BS 8110, they would give you different options which are applicable to those codes. That's columns. Now we can look at beams. We currently have a 600 by 600 square beam. I'm going to taper that so that at the top it's a 900 wide beam, and I hit Control R to copy everything down. And now we have a nice taper on the beam the whole way along. Drop panels. Drop panels can be defined. This is a simple version in terms of the input. So if we were to define a drop panel, for example, at column 2, I could define a total depth of, say, 600 millimeters. Now it's a bit unusual here because you wouldn't put a drop panel on a beam, but drop panels are commonly used for flat plates, and this is how you do it. So you'd normally have it at least, they must be normally 1/6 of the span length into the span in order for them to be counted as a drop panel. So I'll show you what I mean. We know that our span is 8 meters, and so if we take 1/6 of 8 meters, it's going to be roughly 1250. And I'll do 1250 in each direction. I might make it a bit deeper just so it's a bit more obvious. Oop. And here we have a drop panel, and if I show it in plan, it'll be a bit more obvious. There's our drop panel. If I do it to scale, we've got it 1250. Oh, this should be 2.5 meters. There we go. So this is a drop panel. We can also define it as a drop capital, and the difference is a drop panel is included in the calculations, the flexural calculations. So that includes ultimate limit strength, so strength calculations, deflection, shear, and these the difference or the logic is that the panel is wide enough for shear flow to, or for shear lag not to mean that this part of the beam is ineffective. So if I reshape this to a normal scale, you would see that when a bending moment comes in to this, if I do it in elevation, as the bending moment comes in, there is a shear lag that's roughly 45 degrees. So say this triangle here wouldn't be effective, but in this corner, but the rest of the drop panel would be. Whereas if we were to make it a very short panel, it would then become a drop capital. And so let's make this smaller, and let's say this is a meter by 500 by 500. Then you can see that when the beam or the slab meets the drop capital, the step is too steep for that section to work flexurally. There is not enough distance for that shear lag to take effect. But what happens with that as a drop capital is that shear, punching shear is now calculated at this face, as is shear. Although typically, as I said before, you wouldn't be doing a drop panel or drop capital with a beam. This is just to explain the whole design or the options in RAPT. So now you know the difference between a drop panel and a drop capital. Typically, a drop panel is would extend a minimum of 1/6 of the span or more. Otherwise, it would be a drop capital. Now, we just did a very simple drop panel or drop capital, and but we can do a more detailed one, so it can be different dimensions in each direction and also sloped. You just click this magnifying glass and it gives you further options for top and bottom dimensions of the drop capital. Okay, I'm going to delete that now by hitting 0. Now we look at transverse beams. Transverse beams are beams that extend column to column in the orthogonal direction. If you were putting in transverse beams, you would be running a two-way beam run, but we are doing a one-way beam run, so obviously transverse beams don't really make sense here. They can make sense if you are designing a one-way slab and you have transverse beams, and there you would put in, define it as a band or a beam. Now a band, just like a drop panel, is included in the flexural calculations because the width of the band is large enough for shear lag not to discount the section properties in the calculations of strength, deflection, whereas if it was a beam, then the beam ends up becoming quite short and squat and becomes a part of the support, and then that ends up defining the critical section for shear calculations. So if I put in a beam here that's say 700 deep and 900 wide, then that would not be wide enough to be included in flexural calculations. That would be just a part of the support, and if the critical section would be taken from this point here rather than from the column with the face of the column. There are more details on that in the help in terms of how the critical section is calculated, but that is the gist of it. Okay, I delete that now. None. Layers. Okay, RAPT. These next three parts, layers, elements, and steps, some of them overlap in terms of what they can do. So what you can do for one, you can do with the other, but they do have some differences which make them unique, and you may need one or a combination to model whatever geometry you have. Let me start with layers, just to show you what it does. Layers are essentially like a layer of a cake. They just add a layer to the top or to the bottom of the existing layers, and the existing layers are done by default by RAPT. So we have a slab, we have a beam, the slab and the effective beam flange, they are just the defined slab panel, and then we have the beam underneath. So we can add a layer underneath or a layer on top, and we can create that layer so it's right across the whole width or just to one side of it. And when we do, I'll give you an example. Let's add in an upturn layer. It'll be 200 above the top surface. It will be 2.5 meters to the left. I will make it 2 meters wide to the left, 2.5 meters to the left, beg your pardon. And that will give us an upstand, if you like, or a thickening on the left-hand side, and we can then adjust that. You can adjust it so that it is sloped as well, and you'll see that as I change some of these dimensions, minus 2000, you can end up with a slope like that. But the key thing with layers is that they extend the full length of the frame, whereas elements do not. So that's the key difference between layers and elements. Let's delete that layer. Now an element, before I do that, I might just add a step. So if we have a fold in the RAPT run, we can add that. Let's add a step. Now I can add it manually in here by telling RAPT which surfaces we want to change and by how much, or we can click here in the shortcut menu, a full step, a top step, a bottom step, or a general step. So I'll add a full step, and from, I haven't defined the grid reference first, so let's go back to grid 2 and let's put in a step. Now you see you can define it as a flexible step or a rigid step. That is the same differentiation we made between a drop panel and a drop cap, or a transverse band and a transverse beam. So a flexible step will be included in flexural calculations. A rigid step will not. It'll just be assumed to be the same curvature from the one side of the step to the other side of the step. Now we generate this step. Let's have this as 2 meters past the grid line and 200 mils down. And then let's have the bottom of the step only 500 mils into the slab. So we have basically 1.5 meters step. And maybe that's not enough. Maybe we needed a bit more than that if we want it to be a flexible step. So we can come along to our step data. So I think I made a mistake when I entered that dimension. It should be 2 meters. And there we see our slab is a lot, our step is a lot longer. And we want the bottom of the slab panel to step down. And let's say we only want that to step down 500 mils past the column. And for the beam, similarly, we want that to be dropping 500 millimeters past the column. Okay, so now we've got the slab and the beam both stepping at that location. And if we look at the sections, from one section we go to a thickening, and the thickening then stops at this location here. Now you probably would have the slab stepping at a much tighter distance, so we can do that. And let's just add this to be, say, 1800, so that it's a 200 wide step in the slab. Of course, we can also do horizontal steps, so we can in plan step the beam either on this side or that side, and that will change both the loadings and potentially the effective width of the beam. I should explain that when we look at our beam, RAPT will give you and calculate the effective flange width, and the effective flange width is what it calculates its inertias with and its design reinforcement. So this is a simplified version, but if you click the magnifying glass, it'll show you the detailed version for Eurocode. Okay, so we've put in a step, and I might put in an element to show you what that does. Let's add in, you can either add in solid elements or you can add in voids within already solid areas. So let's add in a trapezoid, a solid element. Now you can do this by the wizard, or you can just do it by hand. I'm just going to do it by hand here. When I say by hand, I just mean directly into the data entry. So let's make this an upstand, and we'll make it between grid 3 and grid 4. And we will make, as it's an upstand, so the distance from the top of the slab is actually negative. So we'll go up 400, and we will give it a depth of 400. Now we will offset it, let's say we'll keep it to the right hand side of the slab. So we'll make this 2300, 2500, 500. And now we have an upstand, which we actually need it deeper than 400 because we've got a set down here. So we'll have this as 600. And now we've created an element that extends just for this portion of the run and disappears. Now we can also adjust that or even design it as graphically. So we can just click the triangle here, and that'll allow us to move or change the shape. And again, like everything else, we can create any shape we want. Just note this though, that as we finish this, I'll click OK, and I will go to output, and I will show you the I values for this span 3 to 4. So it's span 1, 2, 3. Span 3, we go to the text output, and I scroll down to span 3, and you can see that our I gross transform section is about 8.7 e to the 9, which is roughly the same as the previous span and the next span. And the reason for that, the reason that there is no real change in the I value is because this element is not within the effective flange. So if I was to move that and put that over the effective flange, you will see that that I value that we had increases in span 3. And we're now 1.68 to the power of 10. So that's increased markedly. And remember that if we have this element out here, it's not going to affect our stiffness, and RAPT will not add reinforcing for this area. It's only adding reinforcement for the effective flange. And that covers frame input.